All right, let's jump right in. What if I told you that you could create a whole bunch of custom AI models without any of that super expensive training? Well, today we're going to look at this honestly shockingly simple technique that lets you literally blend different AI brains together to cook up the perfect mind for just about any task you can think of.
So, right now in AI, you're kind of forced into this tough spot, this fundamental trade off. On one hand, you've got what we'll call the thinker models. These things are the deep, powerful reasoners. They spin up these long, complex chains of thought to get to some incredibly accurate answers. The catch? They are slow and super expensive to run. Then, on the other hand, you've got the sprinter models. They're fast, they give you direct answers, which makes them cheap and really efficient. But well, they can totally whiff on the more complex problems.
And let's be real, for most of what we actually do in the real world, we need something in the middle, right? You don't always need the world's greatest philosopher, but you probably need more than just a quick reply bot. So that brings us to the big question. How can we create a whole spectrum of models that fills that huge gap between these two extremes? And can we do it efficiently? Okay, so the solution they came up with is a technique called model merging. And it's almost deceptively simple. I mean, you literally just take the parameters, the weights of two different models, and you just smush them together using basic math. The easiest way is just a weighted average. So you can just tweak a single number and create a blend that's, I don't know, 70% sprinter and 30% thinker. It's that straightforward. But here's the best part, the thing that's really a game changer. This requires zero additional training. You heard me right. No massive GPU clusters burning away for weeks, no painful fine-tuning. You just do the math. It's basically a shortcut to creating a whole new family of custom models for practically nothing. Yeah, I know what you're thinking. It sounds way too good to be true, right? I mean, just averaging two insanely complex neural networks together, that sounds like a recipe for absolute disaster. Which begs the question, should this even work? At all? And here's exactly why we should be skeptical. Look, we're not just merging a model that knows about biology with one that knows about history. People have done that, it works. No, this is different. We're trying to merge models with two fundamentally different ways of thinking. One gives you the answer straight up, and the other reasons its way there, step by step. So this isn't about adding knowledge, it's about trying to blend two totally different computational strategies. And this brings us to the big technical risk. The paper puts it pretty bluntly. There's a huge risk of creating a completely broken, incoherent mess. In research terms, they call this a high-loss ridge. Think of it like this. Imagine you've got two mountain peaks. The path between them isn't a nice, flat bridge. It's a deep, treacherous valley. Any point you stop in that valley is a terrible place to be. That's the danger here. The middle ground could just be a useless jumble. And let me tell you, the valley between these two models, it's massive. The researchers actually measured the difference between the thinker and sprinter models they used. In what's called parameter space, the relative distance was a whopping 7.9%. Now I know, 7.9% doesn't sound like a crazy number on its own, so let's put that into perspective. Okay, so for context, other successful model merges, the kind that actually taught the leaderboards, they were usually between models with a distance of about 0.5%, 0.5%. The distance we're talking about here is over 10 times larger than that. These two models are just incredibly far apart from each other. They're in different zip codes parameter-wise. So let's just recap for a second. All the evidence, everything we knew, pointed to this being a massive failure. The models are just too different. The stuff that makes one a thinker isn't some little plugin you can toggle. It's a bunch of dense, interconnected changes spread all over the entire network. In fact, get this. When the researchers tried to just trim away 50% of those differences, it caused what they called catastrophic damage. It completely broke the model's ability to even understand language. And yet, despite all of that, it worked. And I don't mean it just kinda worked. It worked beautifully. The results were, frankly, stunning. They tested it on a really tough reasoning benchmark, and as they dialed up the amount of the thinker model in the mix, the accuracy just went up in a smooth, predictable curve. There was no valley of death, no high loss ridge, no catastrophic failure. Every single model they created along that spectrum was perfectly functional. But wait, it gets even better. Seriously. The researchers found something that's kind of the holy grail in this field, a Pareto improvement.
Now, what that means in plain English is that they created new merged models that were better than the original thinker model on both of the things that matter. They got higher reasoning accuracy, and they were cheaper to run.
And the data makes this crystal clear. Just look at this example with the 4 billion parameter model. The original thinker model, it scored 78% on accuracy and used about 17,500 tokens to do it. Okay, not bad. But one of their merged models, it scored a higher 81% accuracy while using only 15,000 tokens. Better and cheaper. This wasn't just about finding a happy medium. No, this was about discovering a brand new point on the spectrum that was actually superior to where they started. That's huge. And just to really hammer this point home, to show how robust this whole process is, the researchers started trying totally arbitrary custom merging strategies. Stuff with absolutely no theoretical backing. They were just winging it. And even those worked. They all created functional models, which just goes to show that the space between these two models is incredibly stable and friendly to this kind of mixing and matching. So, this all leads back to that one massive question. Why? Why did a technique that, by all rights, should have failed spectacularly end up working so well? So well that it actually produced better models? What's the secret sauce here? Well, the paper puts forward this really elegant hypothesis. What they think is happening is that model merging isn't just a mathematical trick. It's actually approximating points along a continuous training path that would exist if you were to train one model into the other. It's almost like they found a way to time travel through the training process. Like you're scrubbing through a video of the sprinter model slowly evolving into the thinker model, and you can just pause and pick out the perfect frame. So think about what that means. Instead of having to do that incredibly long and expensive training run yourself, model merging lets you just jump to any point you want along that hypothetical path. You've got your starting point, the fast direct model, and your endpoint, the deep thinking model. Merging is like loading up an old save file, letting you create any version in between as if it were just an intermediate training checkpoint. And this is the explanation for that incredible, better, and cheaper result. The hypothesis suggests that the original thinking model was actually a bit overtrained for the task. It had already hit its peak performance, and all the extra training just made it generate longer, more expensive, and more convoluted answers. So by merging, they were effectively dialing the model back in time to that more optimal, more efficient sweet spot. Peak performance with way less waste. So what this research really shows is that sometimes the simplest ideas can completely defy what we think we know and unlock some incredible new powers. It proves that model merging isn't just a tool for finding a compromise, it's a powerful, training-free way to actually optimize our models. And it leaves us with this one really fascinating final thought. In the vast, weird, and wonderful world of AI, what other impossible shortcuts like this are just waiting out there for us to discover?